So we are going to discuss a concept of differentiation or differential calculus. And we are going to cover Unit 1, derivative of a function. The derivative of a function, fx, denoted by f prime of x, or df dx, is the rate of change of the function with respect to x, and is given by the notation f prime of x equals to limit as change in x approaches to 0, whereby the function of x plus change in x minus f of x, when we divide by the change of x. If this limit exists for all values of x, now this relation becomes the derivative of a function with respect to x. And now the process of finding the derivative of the function is called the differentiation of the function of x, or we can call it the differentiation by the definition. Now we are going to see it geometrically how we can derive this formula. So geometrically, suppose we have the exponential function, this one is shown by the curve, and we have the second line that's passed through points A and B on the curve. And now we want to find the slope or the gradient or the derivative of the function now, this curve here, by the approximation of the second line by applying the limit. Now what we can do now, for example here, we have our point A, that is x, comma f of x, and we have the point B here, that is x plus change in x, and the value of y coordinate, it is f, then x plus change in x. Now, on starting now, we can try to find the gradient of the second line. So we find the gradient of the second line. That will be now change in y to the change in x is less small to change in y. It means now we find here the change in y, that is y2 minus y1. So, but our y2 now is the function of x plus change in x. Then now we minus the function of x, and then now we divide by change in x here. We look the displacement along the x-axis. So we have x as the starting point. Now after displacement, we have x plus change in x. So we take this minus this, we get the change in x. So x plus change in x minus now x. So now the gradient of the second line becomes change in x minus the function of x over, here it remains, this and this cancel out, so we remain with the change in x. Now from here, we have the slope or the gradient of the second line. Now, for we to have the slope of the curve, we need now to find exactly the slope at a specific point, whereby we need to reduce point B to point A by how? By applying the limit concept where change in x is approaching to 0. So what to do now? Now to obtain the derivative of the function, the limit now is change in x approaches to 0 for all x. For all x, then when this change in x becomes 0, it means now we'll have the derivative, or we'll have the derivative of the curve at point A, where we can say it's like saying now this second line has been reduced to become the tangent line. So what to do here, it means we'll have dy dx now equals to limit as change in x approaches to 0, f of x plus change in x minus the function of x over change in x. So if this limit exists, it means now this second line, the gradient of the second line, now it is transformed into the derivative of the function, where will be the slope of the tangent line here. It means you'll have the new line, that will be the tangent line. The tangent line, that is the approximation to the curve where we obtain the slope at instant point, point A. And that's become now the difference between the gradient and the derivative. Derivative is obtained at instant point, but the gradient is obtained between the interval or between the 2 points. So from there, now we'll have the first principle of differentiation, or differentiation by definition, whereby all these approximations that we have done through limit concept for all values of x, that is what now we call it differentiation process. And now let's see the examples. How do we apply this? So let's switch to the practical examples on the application of the first principle of differentiation. As now the question says, use first principle of differentiation to find the derivatives of the functions. So function number one, we have the function of x equals to x squared. So from here now, we can try to collect the details. We have the function of x, which is less more to x squared. And now remember there in the first principle of differentiation, we have xc plus change in x. So this now becomes, it means where xc from the original function, we just substitute x plus c, change in x. So this becomes xc plus, so this becomes xc, that is xc plus change in x, bracket t square. And then now what is needed? We need f prime, or we can say dy dx. Now on the solution scheme, from first principle of differentiation, as we stated earlier, that is f prime of x is less more to limit as change in x approaches to 0, f of x plus change in x minus the function of x when divided by the change in x. So from our data here, f of x plus change in x, that is this one, and the f of x now is x squared, already provided. So what we need is just to plug them into the relationship. Now from there, f prime of x will be equals to limit as change in x approaches to 0. Now f of x plus change in x we have here, that is x plus change in x square, we minus f of x, that is x square over the change in x. So from here we'll have the limit change in x approaches to 0. Now we expand this one. Here it is, the exponent is 2, so it is simple to expand. We can apply Pascal triangle to expand, or we can just multiply normally as perfect squares. So when you once expand, we'll have the result x squared with plus 2xc, change in xc, with plus change in xc square. Then we minus our normal x squared. Now the whole thing, now we divide by the change in x. So the concept here is to simplify this change in x here. After simplifying, now the change in x that goes to remain, we are going to approximate it to 0, or we apply limit by direct substitution. And now, so we'll have limit as change in x approaches to 0. So this x squared and this x squared once operated now becomes 0. So here we'll have 2x change in x, and we plus change in x squared. So change in x is common. It is found here at this term and this term. So we can factor it out. So as we can simplify with this change in x at the denominator. So it becomes 2x now we plus change in x. It means factoring out, you divide by this term factored out. So once this divided here, it becomes 2x. And once it divides here, it becomes change in x. So it's a matter of simplification. So when we say this time this, it becomes the same thing as normal. And this time this, it becomes the same thing. So this and this cancel out. So we divide by the change in x. So on simplifying now, change in x and change in x will cancel out. So we'll remain with the limit. As change in x approaches to 0, then here we'll have 2x now plus change in x, because this and this cancel out. And now from here, we can apply limit direct. Where change in x, we just put 0. So it becomes 2x now plus 0. So whereby now f prime of x now becomes 2x. So we can say now derivative of the function that was x squared with respect to the independent variable x is less more to 2x. And this now becomes the derivative of the function. So let's proceed with example 2. And that says f of x equals to 1 over x. So we are trying to check on the rational functions. Yeah. So here, let's go to solution scheme. That's the detail that we have here. It's the f of x. So we can write f of x, which is 1 over x. And the other thing now we have, it is xc plus change in x. This one, we're trying to see whether once we introduce the change in x to the function of x. So it is 1 now over, where xc, we just put x plus change in x. So it becomes xc plus change in x. Now from the first principle of differentiation, which states f prime of x goes to the limit, change in x approaches to 0, f of xc plus change in x minus f of x, you divide by the change in x. So all the data that we have, this f of x plus change in x, we have this one, 1 over x plus change in x, and f of x already provided earlier. So it's a matter of inserting them into the parameters. So f prime of x equals to limit as change in x approaches to 0. Now, the value of this, it is 1 over. So that is 1 of x plus change in x. And the value of f of x, it is 1 of x, as we have seen there, then over change in x. So here, we are trying to manipulate here. We are trying to simplify. So the first thing that we are going to do, you find the LCM. You find the LCM, and now later we'll see the way how we can simplify with this change in x here, because we cannot apply limit direct to the change in x without simplifying change in x. We have to simplify first change in x. The change in x that is going to remain, now we can apply limit by direct substitution. So what do we do? We find the LCM. So the LCM here becomes, here our LCM, the LCM here, it is the product of this and that. So it is xc and the xc plus change in x. So this divided by this, we get x times 1, that is x. And now minus, when this expression divided by x, we are going to obtain x plus change in x. So times 1, we get xc plus change in x, but we introduce the brackets. So from there, we operate the numerator expressions. So once operating now, we'll have limit as change in x approaches to 0. So this becomes xc. It becomes x minus change in x over xc, then xc plus change in x. And now remember, this was the numerator expression, but all these we divide by the change in x here. So all these, remember, we divide by the denominator change in x. So that's how it becomes. So here, it becomes limits as change in x approaches to 0. This cancel out, so we remain with negative change in x over xc, then xc plus change in x, and now all these we divide by the change in x. So from there, now it becomes limit as change in x approaches to 0, that this expression when divided by this one, it means now when you change the division sign to multiplication, it means this one now will come to the top. So we reciprocate. It becomes negative change in x over xc, then xc plus change in x. Now we times change in x. So it becomes like that. So from there, limit as change in x approaches to 0. Now we find the way of simplifying now change in x simply. This one and this one now will cancel out. So we'll have negative 1 over xc bracket xc plus change in x. So for at this point here now, we are free to apply now limit by direct substitution. So we are changing x, we can introduce 0 now. So once introduced now 0 to the change in x, no need of writing again change in x. So what we do, it will be negative 1 over x now, then xc plus 0. And here you are allowed to write f prime of x. So it becomes now negative 1 over this now here becomes xc, x times x now become xc squared. So now this now will be the derivative of the function which we had earlier, which was f of x equals to 1 over x. So this now will become the answer. So let's step to example 3, which is f of x equals to the radical of xc plus 1. So we're going to see the other form of equations that involving exponential form or the power form or radicals. So here we have f of x already provided, that is the radical of xc plus 1. And now f of xc plus change in x is less more 2. So here the discriminant x plus 1, where x now we put x plus change in x. So it becomes the radical of xc plus change in x, now plus 1. So from there, how do we find now the derivative of this function that involving the exponential curve? So we use the first principle as already guided. So from the first principle of differentiation, that is f prime of x, which is now the limits as change in x approaches to 0, f of x plus change in x minus f of x over the change in x. So from there we plug everything, the values of this and that, into the function. So now it becomes limit as change in x approaches to 0. The value of this one is the radical x plus change in x, now plus 1, minus function of x, that is the radical of xc plus c 1. Now all these we divide by the change in x. So the concept that is supposed to be applied here, where for we to find the derivative now in the smooth way, we need to rationalize numerator. So on rationalizing numerator, now can simplify everything, and we can be able now to apply limits where change in x now will plug equals to 0 as to simplify and to obtain the value for all values of x where the limit now exists. So what to do, it means you rationalize to the numerator expressions. So it will becomes limit as change in x approaches to 0, that is xc plus change in x plus 1 . So rationalizing factor becomes the same numerator expression, but what we do, we change the operator. So from negative now it becomes, from minus it becomes addition. So it will be
xc plus change in x, then plus 1, we plus xc plus c 1. So now over change in x, we multiply by the same rationalizing factors. Yes. So now we have multiply by rationalizing factor, which are this one. So from there, we can find the way now of simplifying. Now look at the top expression here. There is a way of either multiplying by opening the brackets, or we can apply different of two squares. So from this concept here, a square minus b square equals to a minus b bracket a plus b. So once you try to check our expression here, top expression, where there is minus here, we can apply squares. So once apply squares, this now becomes x plus change in x plus 1, and this one becomes x plus 1 because that square cancel out with this index 2 here. So on applying this, the simplest way of simplifying, it is the best. So now it becomes limit as change in x approaches to 0. So here we'll have x plus change in x plus 1. So we put square. Now we minus the radical of x plus 1. Now square. So that's the short form of writing this expanded. Then over change in x bracket. So here we cannot touch anything. We just leave them. So it becomes x plus change in x plus 1. Now plus xc plus 1. So we deal with the numerator expression until we don't see the radicals. That's the meaning of rationalizing. So then again here, it becomes now limit as change in x approaches to 0. So this cancel out with this one when you express in exponential form. The exponent will cancel out. So it becomes this one minus. Remember here, when you open this one, when you cancel this index and that exponent, this discriminant inside, we need to introduce the bracket so as we can apply this negative sign properly. So we introduce bracket, then xc now plus 1 because this cancel out with that one. Then over change in x, then xc plus change in x plus 1. Now we plus xc plus 1. Now we can open the bracket and operating the like terms. So it becomes limit as change in x approaches to 0. So xc plus change in x plus 1. Now we are going to open the bracket. So negative 1 times x, now it becomes minus x. And negative 1 times positive 1, it becomes minus 1 over change in x, then xc plus change in x plus 1, we plus xc plus 1. So from here, operating the like terms, xc minus x cancel out. 1 minus 1 cancel out. So here we remain with the change in what? In x. So now it becomes, change in x over the change in x bracket, the radical of xc plus change in x plus 1, then we plus radical of x plus 1. Now, having reached that stage, we are allowed now to simplify changing x and changing x. So once goes, we are going to have a limit as changing x approaches to 0. This one and that one cancel out. So it will remain 1 to the numerator, and at the denominator, we'll have xc plus change in x plus 1. Now we plus xc plus 1. So from here, We can apply now the limit direct, where changing x, now we introduce 0. So here becomes 1 now over the root of xc plus 0 plus 1. Now we plus the radical of x plus 1. So now we'll have x prime less small to 1 over. So here it becomes the root of x plus 1. We plus xc plus 1. So it becomes 1 over. So the radical of x plus 1 plus radical of x plus 1, because now the discriminants are the same and the indexes are 2 and 2 here, we are allowed to add the coefficients or the outside numbers, 1 plus 1. So we get 2, then root of xc plus 1. And now this becomes the derivative of the function. So let's also see the constant function. How do we find the derivative of a constant function like this one? F of x equals to 4, a constant number. By using first principle of differentiation, how we can solve this one, how the slope of it is determined. So now we can go direct. The f of x now is provided, is 4. And the f of x plus change in x is less small 2. It means here now, because we need x as the variable, so we can introduce here x power 0. That means 4 is the same as 4x raised to 0, because anything with exponent 0 is 1. So having doing that, also here for x plus change in x, now we can say 4, where x, now we put x plus change in x, but we introduce that 0 exponent. So from there, from first principle of differentiation now, from the first principle of differentiation, f prime of x is less small to the limiting value, where change in x approaches to 0, then f of x plus change in x minus f of x over the change in x. So it becomes limit as change in x approaches to 0. Now, our f of x plus change in x, it is this one. So we introduce there 4, then xc plus change in x. Now we minus our f of x, it is 4x power 0 here. Or we can just say 4. So from there, we divide by the change in x here. So when dealing with the limit, all the constants, we can just factor them out of the limit. So this 4 is constant now, it can stays outside the limit. So it becomes 4 limit as change in x approaches to 0. So here we'll have x now, we plus change in x power 0 minus 1, but this one here we can say x power 0 over change in x. So from here now, we can have this 4 value, then limit as change in x approaches to 0. So here, x plus change in x raised to 0, the expression now becomes 1. And the x raised to 0 also, the term becomes 1. So it will become 1 minus 1, which now we get 0 over change in x. But we can simplify here by introducing, expressing this 0 in the other way around, where we can have change in x. So we can do like 4, then limit as change in x approaches to 0. So this one is the same as say 0 times change in x over change in x. So once simplifying, change in x and change in x now will cancel out. Then it will become now here, we'll have 0. So limits for a constant number 0, it become 0. As what we say, limit of a constant is constant. So here it becomes 4 now, And the value of this limit here now, it will become 0. So at the end of the day, we'll have 0. So this now mark the derivative of a constant number. So this will be the slope. But also, if you want to go in the other way around, we can apply here L'Hopital's rule, where it can help to simplify, and you can get the same value. So from there, that's the derivative of the constant function. So for any constant function, when we find its derivative, no matter we are using which technique, either the first principle of differentiation or other techniques in the concept of differentiation, it is always 0. So up to this point, this marked the end of our session. Today we have seen the differentiation concept or differential calculus in the unit called the derivative of the functions, and how we can apply the first principle of differentiation on solving different problems regarding the exponential functions and the other functions. So for more sessions, keep watching our channel.